Hi everyone, welcome back to our class. Before the start of the class, I have two announcements that I want to confirm with you. So the first announcement is that assignment 3 will actually due in 1 week, basically by the start of the next class. Please keep in mind that you don't want to submit your assignment 3 late. And the deadline is within 1 week. So the second announcement is that project proposal will actually do within 1 week, basically like 5 weeks from now. Basically, at the end of week 8. Currently, we are in the eighth week for this fall semester. And the deadline will be on October 30th, on the night of October 30th. By submitting the project proposal, just send an email to the TA. So these are like two very brief announcements. And for today, we are still going to talk about dynamic programming. So basically, for the last time, we talked about dynamic programming, and basically we gave algorithm for the weighted interval scheduling problem, for the segmented least square problem, and also for the very important knapsack problem. So the knapsack problem really has a lot of applications. For today, we are going to continue with and actually also finish dynamic programming. So today we are going to talk about another 3 examples: sequence alignment, shortest path, and also negative cycles in a graph. So because mostly for graph problem, we are talking about positive ways, but actually for graph problem, there are also problem about like negative ways and corresponding some studies along that. Okay, so let's get started. Let's start with the sequence alignment problem. So I guess basically for the as you can see in the class, I think in general we want to talk about problem from different categories. I guess you probably you work on different aspects of computer science. I guess it's probably maybe let's also work on a few different directions. So for sequence alignment, so basically so for sequence alignment, we study strings. And in particular, how similar to strings. So for instance, I guess there are like English words, for instance, there are like occurrence, excuse me, occurrence, an occurrence. So I guess there are like English words like this. So you see, actually, these two words, they're actually quite close to each other, but they are not exact. So basically, we need to think about, in general, this is a very important problem, in dealing with strings, that basically how similar are they and actually how different. And maybe, for instance, maybe we want to think about a problem that if two strings are similar but not exact, maybe you want to think about what is the best way that you can align strings. So for instance, maybe we can think about maybe we can align like this. So we just put it in this kind of thing. We just firstly write them down. Occurrence. And maybe just occurrence. So I guess if you just write down these two English words like this is unfortunately probably not the best way, to match the strings. So for instance, we just look at the places where like the first row and the second row, they are different. So these are basically O's. So that is probably fine for us, but C's, and U's, those are probably fine for us. But maybe actually there are some issues along this. So we see that basically, for the later part of the string, this is a mismatch because for the first row we have an A here, but for the second row we have an R. So of course A not equals to R. So this is not something so good. Maybe for instance, we can also look at this and also look at this. Maybe let me actually make this space a little bit larger. Like this. Like this. So basically at last, we have a place where actually the first word already ends, but for the second word, there is a letter here. Typically in this case, we just draw a brief line here. So we can say that for this case, we basically have 4 mismatches. When there are letters and the letters are different, we just call they are like a mismatch. So actually for this example, we have 4 mismatches, and actually there is 1 gap. So by gap, I mean, actually we just ignore something here. So basically, I mean, maybe for the first line, there is just no letter here, but the second line, we actually have a letter here. So we call this that as a gap here. So maybe we want to think about this. I mean, in general, I mean, this is an example where we have mismatches and gaps, but maybe there is a better way that we can hopefully arrange these letters in a better kind of sense. So maybe for instance, maybe let me move it a little bit here. So we can also consider something like this. So let's maybe for the second word, we still like write occurrence. Like this. But maybe for the first word, I mean, in general, maybe we can think about like occur. So I guess in general, we are talking about maybe we can have some gaps, but maybe, I mean, it is not necessary that the gap always appears at the end. Maybe we can at the middle, we have like a gap like this. So in this sense, I mean, you can imagine that this is probably better than the first example. Maybe for instance, is in particular, for this example, we are actually having only one mismatch. And actually one gap. So any questions? So you can apparently see, I mean, we are actually, for the first example, we have 4 mismatches and 1 gap. And actually for the second way of aligning strings, it is definitely better because the number of gaps is the same. They are actually, both of them are actually only having 1 gap. And actually for the second example here, we actually only have 1 mismatch. And actually the first way after we do this, we actually have 4 mismatches. So this is not so good. But maybe, I mean, I think especially maybe let's first mention a few applications for sequence alignment. So the sequence alignment is just so important in general, I think, especially for instance, in coding. I mean, in general, in Unix systems, there is a function called diff. I mean, I guess maybe some of you are probably already working on research papers. And typically in research papers, maybe you want to revise a paper. You want to use the diff command. I mean, for instance, in this Apple laptop or maybe a Linux system, you can use the diff command to make a comparison between your current version of your manuscript and like earlier versions. So basically the diff function is actually based on sequence alignment. And actually, for instance, you can definitely imagine that in general, sequence alignment is like a very basic problem in pattern recognition. And in general, pattern recognition has a lot of applications, for instance, like in natural language processing, in computer vision, graphics, etc. And also very importantly, a sequence alignment problem is also very important in computational biology. I guess maybe the computation, I guess the spelling is wrong, computational biology. So in computational biology, we just deal with DNAs and RNAs. And in that case, I mean, the string are typically just composed of A, C, T, and G in general. Like so in general, the sequence alignment problem is also actually of very general interest. I mean, spanning from different areas. We really want to have a good algorithm for the sequence alignment problem. But I guess in general, I mean, thinking about all different kind of applications, maybe sometimes, I mean, the cause of mismatches and gaps, they are probably different. I mean, for instance, especially for this example, we can actually give an example that actually, I mean, we can actually give a way of making an alignment there there's totally no mismatch. So what do I mean by that? So maybe we can think about this example. So we have this occurrence. Maybe we have the A here. Let me see. And for the second line, maybe we can do this. So actually there's a two spacing for the first occurrence, and actually for the second line, for the second row, we actually also have two spacing for like different positions. So for this example, we actually know that there is actually 0 mismatch. Because as long as both lines, they have letters, they are actually matched. But for this example, we actually have 3 gaps. So this is something we want to notice. I think especially, for instance, in computational biology, I mean, in general, we want to run like a sequence alignment problem. Maybe we want to fix Maybe for instance, if two DNAs are different, maybe we want to make a fix for that. And typically for a lot of applications, the cause of mismatch and gap, they are different. So that is the reason why we want to be a little bit more careful along this. Although maybe for some examples, if they are the same, you just like regard them as the same. But maybe we want to be a little bit cautious here. Maybe for instance, for some applications, maybe one mismatch, one gap is better than having zero mismatch and three gaps. But maybe also for some special cases, it's also the other way around. So that is one reason we actually make this clear that basically for examples, we can have like mismatches and gaps. So any questions about like the general discussion here? Okay, I think this is basically like an intuition for this sequence alignment problem. So maybe let me actually give you more precise definitions, and we will then describe the algorithm that we are currently having. So definition. So basically we define a definition called edit distance. So the definition of edit distance is actually specified like this. It is actually defined as the sum of gap and mismatch. So basically to characterize all these kind of things, basically we have like a penalty. We have penalties for gaps and mismatches respectively. In particular, where actually a gap penalty is actually delta larger than 0 for each letter. And actually also on the other hand, a mismatching penalty. I think here we can be a little bit cautious here that in general, we can call the mismatching penalty is a function called alpha PQ larger than 0, where we want to consider the mismatching between letter P and letter Q. And of course, saying this is a mismatch, it must mean that P is not equals to Q, or otherwise we can just like say alpha PP equals to 0 for arbitrarily P. So for instance, maybe we can just like write down the cause for the above examples. So for example, for the first alignment, I guess I should use this. Actually zoom out a little bit. So what is the penalty for the alignment first? It just follows right follows the definition because we have like a mismatch between A and R here. So that is actually we have like alpha AR here, but actually there is a mismatch between A and E here. So we actually have like an alpha NE here. And actually there is a mismatch between C and N here. So we have like alpha CN. Oh, here actually we also assume that in general, I mean, alpha PQ and alpha QP here. So I mean, we probably are not so sensitive about like the difference, I mean, between whether it appears in the first letter or the second letter. I mean, this is, I mean, in general, if you want to talk about sequence alignment, you always have your own way to make the model, but I guess we are actually basically going to adopt such kind of a model. Nevertheless, I mean, let's continue with the example for the first alignment. So basically, we have alpha AR plus alpha NE plus alpha CM. And actually, of course, we are going to plus an alpha EC here. And basically for the last line, I mean, for this gap, we are a little bit, I mean, not so careful. We just write a delta here, because E is actually matched with nothing. So basically there is a gap here and we just plus a delta. And similarly, we can also think about maybe, for instance, alignment 2. I mean, for alignment 2 here, it is actually quite clear that we only have one mismatch and one gap. So basically here, the mismatch is actually alpha AE. And actually, the gap is basically delta. And also for alignment 3, we actually have 3 delta. Okay, so any questions about this definition of penalties? Okay, so let's get into the the algorithm, basically the problem and corresponding algorithm that we want to give here. So another definition we are going to give here is that in general, I mean, we can then basically we describe alignment. So an alignment M is a set of ordered pairs. Now we see they are actually X, Y actually are mapped to connected to YJ such that each item occurs in at most one pair. So basically, we are having basically a sequential string here, and actually each item occurs basically at most one of these pairs. And actually, they're very important. There is no crossing. I mean, because it is sequential, we cannot like switch the orders here. So basically, there is no crossing where we say, I mean, we can say this in a more rigorous way. So where we say pairs xi, yj, they are actually and also on the other hand, xi prime, yj prime, they are cross. They're crossed if I is actually smaller than I prime, but j is larger than j. And actually, basically having this kind of formula, we just like want to be clear about like what indexes we are talking about. And basically, this is just like a formal way we want to state that there is actually no crossing here. And actually, we are talking about like a sequence alignment problem. I mean, sequence from left to right without crossing here. And actually having this formula, we can basically say that the cost of M is then basically the summation of all the alpha xi yj. We're actually xi yj. They of course they need to belong this alignment. And also on the other hand, we should be focused on the case where xi yj there actually is a mismatch. Okay, so this is basically a part where we have basically we compute the total penalty of the mismatch. And also definitely on the other hand, we need to be careful about the gaps. So basically for the gaps, we just plus delta times the number of I such that xi unmatched. And also plus delta times the cardinality of I where yi unmatched. Okay, so this is just a very formal way that we want to write down the penalty here. I mean, we want to think about, I mean, in general, this kind of alignment, I mean, xi, yj, and whether it is, if it is inside, then actually x, y, ij gives a mismatch. You just want to compute the corresponding, the summation of such kind of alpha xi, yj. And basically, on the other hand, we need to take a good care about the gaps. And basically, we need to compute, we need to basically have this delta times like all the i's such that xi's are unmatched, and also on the other hand, delta times all the i's, the number of all the i's such that y is unmatched. So I guess if this is still a little bit abstract, let's see a specific example. Maybe for instance, in computational biology, maybe for instance, we have like a piece of DNA, which is like CTA-CCG. And also on the other hand, maybe it's a piece of DNA, which is, for instance, TAC, ATG. Maybe let's think about like this example. So maybe we want to, I mean, maybe we can like take a very brief think about how, for instance, we are going to give a good matching for this. I guess, for instance, you can clearly see that maybe there's like a TAC here, there is a TAC here. So maybe this is a pattern that we want to actually pursue here. So for instance, maybe let's follow this and think about something like this. So it's like CTA, I mean a C here. So there is a G here, and actually there is a G here. So maybe like a possibly a good way to do this is that maybe we want to actually have like a C here, have like a G here. So it's like a G here, and maybe it's like a T here. So maybe we by doing this, we want to create as little, I mean, a gap. I mean, as little as few mismatches as possible, and maybe although maybe this can potentially bring into some some of the gaps here. So maybe this is probably still something fine here, but in general, maybe by doing this, basically we are having like a two string like this. So basically for this construction, I mean, basically we are going to have gaps here, and actually there is one mismatch. So basically this is a mismatch. And actually we can say that basically we have like basically, I mean, we also need to figure out what are the x's and the y's here. So basically, by saying like this, so basically, this is the first string. I mean, it's basically x1, x2, x3, x4, x5, x6. Basically, here is y1, y2, y3, y4, y5, y6. So basically, the matching here we are actually giving is that basically we actually left x1s here alone. So basically, x1 does not appear in this matching here. So basically, we are going to have x2, y1 here, and of course, we are going to have x3, y2 here, and actually x4, y3 here. And I mean, we have x5, y4 here, though this is a mismatching, and we are going to compute this later. So what the y5 here, I mean, the t here is actually left alone, and actually at the end, we are having x6, y6 here. And actually, what is the cost of this example? I mean, the cost of this m here. So the cost of m here, we basically have one mismatch and actually two gaps here. So actually, the cost is that basically we are going to have an alpha. I mean, the mismatch is between a and c, so we just write alpha ac. And because we have two gaps here, and this is alpha ac plus 2 times delta. So is there any example? I'm sorry, is there any question about this example and actually the definition here? Okay, so this is basically the sequence alignment problem that we want to study here. And I guess, of course, after having this definition and actually having a definition basically for the sequence alignment problem, we can then ask about the goal here. So the goal here is basically that given two strings. I mean, given two strings, x equals to x1, x2, xn, and y equals to y1, y2 until yn. Find the alignment of minimal cost. So this is basically the sequence alignment problem that we want to solve. So maybe let's actually take a very brief break here and think about, I mean, if we want to design a good algorithm, what we can actually do here. So we can clearly see that this problem, I mean, at least from my perspective, this is probably, I mean, it's not so clear to me how you can solve this by like a direct greedy algorithm. Because for instance, if you look at, for instance, like the end of the strings, there can be like easily like mismatches, and you can definitely imagine that maybe you have some local greedy strategy, but maybe like a local greedy strategy is not going to give you the best solution. So for instance, maybe let's look at the first example of occurrence and occurrence here. So maybe at the beginning here, you give like a very good match between the first few letters, but at the end, I mean, you really got a lot of mismatches. So this is definitely not something you really want here. And maybe you want to, I mean, at least like a trivial like greedy strategy is probably not going to work. So you are probably going to need to think about this more carefully. And also this problem, at least to me, does not sound like a divide and conquer problem. I mean, maybe you want to, for instance, cut the problem in the middle. But here, I mean, it's basically like shifting the string here really causes a lot. It's not like, I mean, this problem is also, it's not really having like, for instance, if you like have like a good algorithm for one part and a good algorithm for the other part. And basically the merging is going to be very painful here because you can actually switch the strings by one bit and actually significantly change the number of matchings here. So that is to say this problem somehow is, I would say it's more global instead of local here. So it's probably basically for like a direct greedy strategy or divide and conquer strategy is probably not going to work so well. And basically to solve this problem, we are probably going to borrow the strategy of dynamic programs here. And basically we will see how actually this is going to work well. So basically for this problem, we also need to be a little bit careful because in general, I mean, as I just mentioned, I mean, shifting the string even by 1 bit is actually going to significantly change the problem. I mean, actually also going to significantly change the cost. So maybe we want to think about how we want to give a good model here. So basically, I guess, I mean, in general, for instance, for the dynamic program, I guess it is very important, for instance, in the knapsack problem. So in the knapsack problem, we actually first talk about a failed attempt, where basically we only have one parameter that basically characterizes the weight. But actually that is not going, characterize the number of items that we have been going through. But actually this is not going to work because basically for the knapsack problem, you also need another register to store the current weight here to make sure what you can do next. So here, I guess, I mean, at least one thing that you can think about is that, I mean, because both strings they're actually changing and actually shifting up, add of the string by 1 bit is going to significantly change the story. So this is basically something you can imagine. So I guess it makes a lot of sense that maybe even if you want to solve this by dynamic program idea, maybe you want to have at least like 2 parameters. I mean, maybe for instance, like one parameter to save something for the first string and maybe the other parameter to save something for the second string. So actually along this, we basically do this. So basically we define the OPT of ij to be the mean cost of aligning strings. I mean, basically, we want to have some kind of truncation for this. So basically, if you have 2 parameters I and j here, we want to consider like a corresponding basis defines the mean cost of aligning strings. I mean, x1, x2 until xn. And also for the y side, it is y1, y2 until yj here. So this is something very natural that we want to consider, that maybe we want to consider such kind of OPTIJ function. And of course, the minimum cost is just going to be OPT at end here. But I mean, basically for dynamic programs, we need to consider, basically need to construct like a relationship between different OPTs. So basically we need to think about, I mean, what is the relationship between this OPTIJ and maybe for instance, smaller i's or smaller j's. So this is basically something we need to think about. So basically, I mean, we need to take a close look. I mean, how actually we are going to decompose the problem. And I think in particular, I mean, for such kind of problem, it makes a lot of sense, like at least from my perspective, that you want to think about maybe, for instance, how the beginning of the string, or maybe how the end of the string, they actually align with each other. And here, since basically the I and j's, and actually we are talking about like all the way to the string, to the xi and yj here. So maybe, I mean, for the ease of having the indexes, maybe we can consider, I mean, the alignment of the strings at the end. So basically, for instance, we consider like all these kind of cases. So case 1 is maybe, for instance, OPT matches xi, yj. I mean, this is really a convenient case for us because if OPT is actually matches xi yj here, we can make the following conclusion that we are going to pay the mismatch for xi yj. So basically, I mean, as I just mentioned above, I mean, to make our life easy here, we can always say that, I mean, if the 2 letters they are the same, we can always pay a cost of penalty 0 here. So I mean, in general, I'm saying that pay mismatch for xi yj here. I mean, if they are the same, you just pay a penalty of 0, which is good. I mean, but if they are different, you just pay the corresponding value of this alpha xi yj here, which is basically always the same. But nevertheless, I mean, in general, I mean, if the OPT actually it matches xi and yj, you're always going to pay the mismatch for the mismatch penalty for xi and yj here, and then we are going to pay. I mean, after that, it is going to be the mean cost of aligning x1, x2 until xi minus 1, and also y1, y2 until yj minus 1. So I guess this is definitely imaginable, and basically for the first case, this is really like an easy case that, I mean, in general, I mean, if OPT matches xi, yj, we are basically having this cost. But I think the next, I mean, we also need to think about, of course, I mean, for dynamic program, we need to think about all the possible cases. So maybe, for instance, it can be the case that we call this case 2a, that OPT leaves xi unmatched. That is basically saying that maybe you have like a string here. Maybe you have like a string here. This is X string, this is a Y string. But the X string is actually longer than the Y string. I mean, maybe for instance, after that, there are actually going to be some gaps here. I mean, at least this is basically the place. This is basically Xi. I mean, there can be, there can be like several gaps here. We don't know. We just don't know. We just know. I mean, if Xi, Yj, they are not matched, there is definitely the case. I mean, either Xi is unmatched or Yj is unmatched. I mean, I'm talking about the case where Xi is unmatched. I mean, there are definitely going to be a gap here. There's definitely going to be a gap here. And maybe there are also something else here. We don't know. But nevertheless, I mean, if the OPT leaves Xi unmatched, we basically know that we are going to pay gap for Xi. And on the other hand, the mean cost of aligning the rest, which is actually going to be x1, x2 until xi minus 1. And for the y part, it is basically y1, y2 until yj here because we didn't make any change to the y's here. So this is actually the case 2a. Maybe let me actually make this look a little bit squeezed. So basically, this is the case 2a here. And of course, on the other hand, we are also going to have the case 2b, where actually OPT leaves Yj unmatched. That is basically saying that the X string is like this and the Y string is like this. Actually, finally, Yj here is longer, and there is actually at least one gap here. So basically, for this case, we can imagine that we are going to pay a gap for Yj, and actually a mean cost of aligning x1, x2. We didn't make change to the axis, so it's actually until xi. And also on the other hand, for the y's, it is at y1, y2 until yj minus 1. So what can we make the conclusion here? So basically, the conclusion is that, for example, of OPT ij here, we are actually always going to a smaller coordinate. I mean, from ij here, we either go to I minus 1, j minus 1 for case 1, or we go to I minus 1, j, I mean, for case 2a, or we go to I, j minus 1 for case 2b here. And also, it is quite clear that OPT 0j actually equals to j delta, and also OPT I0 equals to L delta. Because if one of the string is empty, you just cannot do anything. It's just like everywhere is a gap. This is basically the thing here. So conclusion that basically, if we want to think along this dynamic programming idea, is that basically we know OPT Ij, it actually equals to j delta I delta if I equals to 0, if j equals to 0, and otherwise for the really interesting case, it is going to be the minimum of the alpha xi yj plus opt I minus 1 j minus 1, and also the mean of delta plus opt I minus 1 j, and actually lambda delta plus opt j sorry I j minus 1 if ij is also feasible. So any questions for this discussion and the conclusion? So this is basically how we are going to use the dynamic programming idea to solve this sequence alignment problem. So I mean, having this basically this relationship of the OPT, I mean, it is very simple to actually write down an algorithm for this. So we can clearly see that we have an algorithm like this. So we just call this algorithm to be a sequence alignment. where the input we have is basically m n x1 until xm, y1 until yn here. So basically for I from 0 to m, we are going to have mi0. So basically we are still going to use this memoization trick that basically we are going to have an array to save all the values. So basically for I equals to 0 to m, we are going to have an array whose value mi0 is stored as I delta here. And also furthermore, for j equals to n 0 to n, we actually are going to have the value of m0j equals to j delta. Maybe let me actually make this. So that goes into the main interesting part of the algorithm. So basically, then we have the case where ij there actually at least 1 here. So we do that for actually it is a double loop. So let me write down 2 fors here. So for I equals to 1 to n, and actually for I think the I part should goes to m. For I from 1 to m, and also on the other hand for j equals to 1 to n, we are going to have the values of mij equals to the mean of alpha xi yj plus m I minus 1 j minus 1 delta plus m I minus 1 j delta plus m I j minus 1. And this is basically by finishing like this. And finally, we are going to return the value of m. Okay, so any questions of this sequence alignment algorithm? So let's take a look at it. I guess this should be relatively clear, right? I mean, I guess the algorithm, the structure is actually quite simple. It's just that we need to carefully think about this problem and what is the relationship between different OPTs. And basically this line is like the most important line of this algorithm. And basically based on our discussion, we clearly see that the cost of this sequence, the OPT of this sequence alignment, depending on the case, whether actually at the end of the string, xi, yj, they are matched, or actually the OPT leaves xi unmatched, or leave the yj unmatched. We are actually going to have these 3 cases. We are actually surfaces and we take a minimum among this, and actually we can solve this sequence alignment. So looking at this algorithm, I guess it is very clear that this algorithm takes OMN time and space. This is basically because the size of this array, this array has size m times n. And actually, basically for a computation of each step, basically each step in this double for loop, it is just the minimum of 3 numbers, and this is just an O1 cost. So overall, it is clear that the overall time and space complexity, it is basically O of m times n. Okay, so this is actually based on a very first observation that is actually quite intuitive that the overall time and space complexity is O of mn. But maybe we can make some further observations here. In general, maybe for some dynamic programming problem, we want to think about whether we can save the time or space. I think it sounds a little bit difficult for this problem to save the time complexity because you probably really need to go through all the arrays here. You probably really need the value, from M00, M01, etc. For basically for all the i's and j's, that I is smaller than m and j is smaller than n to actually construct the value of m's here. So basically you can imagine that the time complexity here sounds very difficult to be saved. But for the example, basically for the next like an hour or so, basically we want to talk about whether we can improve the space complexity of this problem. And basically, I mean, for this sequence alignment problem, not only because this is an important problem, I mean, as I just mentioned, with a lot of applications, but I think this problem I'm going to introduce is going to be a showcase where basically how we can save the space complexity of a lot of dynamic program problems here. So let's talk about that. I mean, why do we want to actually, I mean, actually how is like a good way that we can save the space complexity? So the observation. An observation that we can actually make here is that actually the recursion. I mean, basically looking at this, a very important line here. I mean, this is the line of recursion that we are talking about. So basically for this recursion, basically in each iteration, so in each iteration, it actually only calls for those in previous column or current column. I mean, here suddenly appears as the words, I mean, rows, columns. I mean, this is probably a little bit, I mean, confusing. So let me actually draw a figure that is probably going to be more intuitive. So let's draw like actually a two-dimensional grid like this. So at the beginning, we are going to have like a 0, 0 circle here. So we are basically subsequently, that's going to have, for instance, something like this. And actually, so what are we doing here? So basically, we are seeing the rows here. They're actually x1, x2, x3, etc. I mean, well, I mean, it's just like maybe we draw these numbers to show the example. But in general, I mean, for instance, assume that we have an example. Maybe, for instance, the length of x is 3. Actually, the length of y is 5. So what do I mean by that? So in general, we want to think about, I mean, basically how we want to compute this circle. I mean, the value of this circle. So basically, we clearly know that we can actually draw like lines like this. And basically lines like this. And basically, we can say that the weight on the lines is basically delta, 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 delta. So basically, you clearly know that the values here is, for instance, a delta here. And basically for here, it is 2 delta, 3 delta, 4 delta, 5 delta, etc. Basically for this. And basically for this line, and basically you can clearly see for this line, I mean, I'm just talking about the cost, I mean, the OPT of 0 and 5 here. And basically, for instance, let me actually finish the circles here. So basically, for instance, for this, it's just like the cost. I mean, the cost of the between x1, x2, and actually y1, y2, y3, y4, y5 here. So it's basically for OPT, the value of OPT 2, 5 here, and here, for instance, is the OPT of 3, 5 here. So we can basically draw like a directed graph like this. Basically, the very first row and the very first column, we always have the deltas here. But actually, we can have like some rows here. And basically, we can say that this is basically, we are having like an alpha x1, y1 here. And actually, I mean, all this, I mean, all things in the rows and columns, they are actually always delta. So basically, let me finish this. So basically, for all the rows and columns, we are actually going to have all them to be deltas. But basically, I mean, for the diagonal edges, I mean, basically edges like this. And that's basically going to be this weight. Basically, we, for instance, like here, we are actually drawing this to be alpha x1, y1 here. And also, you can imagine that for this, for the next line, it is going to be alpha x2, y1 here, etc. So basically, you can imagine that the computation of this problem is actually finished on this two-dimensional directed graph here. That basically, you just go through the first line here. I mean, after you go through the first row, or maybe I think the observation here I'm seeing in the column. But after actually, if you go to the first column, I mean, you can build the second column only using the first column. I guess this is actually transparent. I mean, if you want to build this, you only need to look at the values from the previous column and actually look at it from the previous column. You just look at them from top to down. Basically, you can just like fill out the values. I mean, basically, this value is depend on this, and this value is actually depend on the 3, and you know that. And basically, this value is actually depend on the 3, and you also know that. So basically, it is actually relatively straightforward that we can see that recursion iteration actually only calls for those in previous column or current column. Or we can actually also say similarly, I mean, basically rows in previous rows. In previous rows only calls for those in previous rows on, I think the English is a little bit on the current column. In previous column and no, I think I want to use the word and. I mean, basically, I'm saying that basically you want to compute this. I mean, compute this value based on the previous compute this value based on the previous column, and basically this based on the previous column and the current column and the value above that, etc. So I think this is the correct English, and basically only calls for those in previous column or the current column. Yeah, similarly in previous rows and the current row. Okay. So this is basically one observation that we have, and basically, I mean, we actually let's also summarize by this. So basically, I mean, by saying that this observation is just like the trick is that we store a layer and actually compute the next layer from top to bottom. And actually, from this perspective, we can clearly see that this we only actually if you only need the value of the cost. I mean, basically, the value of the cost is basically stored on each of the vertices. Then basically, we can significantly improve the space complexity from m times n to actually the minimum of m and n space of SS. So basically, this is a quick conclusion that we can get here. So any questions for this observation and the corresponding discussions? So basically, you can clearly see that there is an idea of actually refreshing the memory here. I mean, if each time we basically it suffices that we only store 2 columns. I mean, for instance, at the beginning we only have the first column, and when it goes to the second column, we only have the values of the first column and the second column. And when we go to the third column, we only have the values of the second column and the third column, etc. And actually, at the end is basically going to be the, I mean, if the value of y is, if the length of y is basically n here, then basically this is basically going to be the n plus 1, And basically at the end, we can only have, I mean, the nth column, n plus 1th column. Or maybe, for instance, if the on the other hand, we can have the only the nth row and the n plus 1th row here. So basically, this is a quick idea that we can clearly see that the space complexity can be improved to minimum. So I mean, and I think on the other hand, I mean, on the other hand, we notice that this is only actually a calculation of the value of the cost. I mean, basically, we just recover the values, but I mean, the value is not actually the measure itself. I mean, we basically need to actually discover what is alignment. I mean, in general, in a lot of applications, I mean, I only tell you the value of the optimal penalty because you're probably not going to be satisfactory with that. I mean, in general, I mean, a question that we can ask is that, what if we want to know, and actually we want to recover an optimal alignment Or another way to see this is that whether we can actually recover like a path from corner to corner. I mean, from actually the very top left corner to the very bottom right corner. Okay, so let's continue our discussion after taking the break.